Hi, this is Dr. Collins Jones. Welcome to segment 5 of my video series on manual cell counting and cell density calculations. In this segment, we're going to provide two more examples of how to calculate the percent viability and the cell density or cell concentration. The second one, I hope you'll pause the video and work it out on your own before you observe my solutions. And then we will also address how to deal with when your cell suspension is too concentrated and you need to estimate a dilution factor. That'll be the last couple of examples. So let's get started here. Here's our problem. Determine the percent viability and the cell density, that is the number of cells per mil, given the following data. A 0.500 mil aliquot of cells was removed for counting from a T75 flask which contained 16 mils of media. 50 microliters of the aliquot, that is of the 0.5 mil aliquot of cells, was removed and diluted to 0.200 mils or 200 microliters using a balanced salt solution. Then 50 microliters of this diluted cell sample was diluted with 50 microliters of trypan blue. And then after 3.5 minutes, we counted 3 squares, right? So before we get into the actual calculation of percent viability and cell density, just wanted to do a quick review. You guys should already know this, so you may want to fast forward, but just a quick review of how to convert milliliters into microliters. We should all know this, but just in case, here we go. So 1 mil equals 1,000 microliters, and to convert milliliters to microliters, the number of microliters is equal to the number of milliliters you have times 1,000 microliters per 1 mil. It's just a simple conversion. So in the case above, we have 0.200 mils times 1,000 microliters per 1 mil, or 200 microliters. And the reason I wanted to spend just a second on this is to encourage you to check the volumes to make sure the units are identical for all the volumes. The volume units must be the same. And generally, when we do cell counting calculations, the unit of volume is in microliters. All right, so let's start the process of calculating the percent viability and the cell density. So the first thing we need to do, right, is count the cells in squares 1, 2, and 3. So here's square 1. We're going to draw our imaginary counting box around the square, right? And then knowing we've done that, we're going to exclude all the cells that are outside the box, right? We only want to count the cells that are in the main square and the large square. So we've done that. Now we're going to follow our little counting pattern inside the box and count the number of cells, okay? And when I counted this, I got 21 total cells and 3 dead, that is the blue cells are the dead cells. So that's square 1. Square 2, same thing. Draw your imaginary box around the counting square, okay? Exclude the cells outside our counting box. Follow your little visual pattern and count all the cells. And here I got 24 total cells, 3 of which were dead. And then I'm calling this square 3, and I think in a previous slide I called it square 4. It really doesn't matter. But again, exclude the cells outside our counting box, count inside the box right here, and we're going to count up. I counted 23 total and 4 dead. So we've done the cell counts, right? This is what you would be obtaining by looking through the microscope at the hemocytometer loaded with the cells. And we do a quick check. All of these squares give us between 20 and 50 cells, so we are in the right range. We don't need to worry about any further dilution, all right? And so if we then add the totals up, we have 68 total cells, right? 21 plus 24 plus 23. We have 10 dead, 3 plus 3 plus 4. And then we have 58 live cells. That's just 68 total cells minus 10 dead cells. And we want to remember that we counted 3 squares. So now we're ready to calculate the percent viability. I always like to write down the equation that we're using. This helps me to remember it all the time. It helps me to ensure that I put the numbers in the right place. And if anyone is auditing your work or grading your work, if you're a student, it just makes it easier to see what you've done. And that means that people won't look as hard at your work if they can follow it easily. Okay, so percent viability is equal to the number of live cells divided by the total number of cells times 100%. So we just have to plug the numbers in, right? Don't need to worry about dilutions or anything else. It's just 58 live cells divided by 68 total cells times 100%. And the percent viability then is 85.3%. Again, we use 3 significant figures in our cell counting calculations just by convention, and that's our answer. Okay, so that was pretty easy. Let's go to calculating the cell density or the cell concentration. Okay, so again, I like to write down the equation that we use to do this calculation first, just to make sure I plug everything in the right place in the right order. So the number of cells per mil is equal to the total live cells divided by the total squares counted, right, times any dilution factors. And here, when you read through the problem, we did 2 dilutions. Dilution 1, we used the balanced salt solution, right? And so if we look at this, we took 50 microliters out of this 0.5 mil aliquot of cells, put it into a new microcentrifuge tube, and then we diluted it to and so 2 means final volume, to a final volume of 200 microliters with our balanced salt solution. So V2 is going to be 200 and V1 will be 50. The second dilution we did was our trypan blue dilution, right? And so here we took 50 microliters of the diluted cell sample from here, from the BSS. So we're doing another dilution, and we're diluting it with, right? We're diluting it with 50 microliters of trypan blue. So now we have to add the 2 volumes together. And for our trypan blue dilution, then our final volume will be 50 plus 50 microliters, or 100 microliters final volume. And again, V1 is 50 microliters. So now we have all the information we need to complete this equation. So we're going to have 58 live cells, right? That's what we counted from the hemocytometer counts. We did it over 3 squares, so that's the total squares, times 200 over 50, right? That's our first dilution with the balanced salt solution. And then times 100 over 50, that's our trypan blue dilution, times the hemocytometer correction factor. So we just multiply this out, and we get 1.55 times 10 to the 6th cells per mil. Again, 3 significant figures for our cell density calculations. All right, so next problem. Again, I'm going to pause here for a second, and you should try to work this out on your own and then see if your answers agree with mine. Okay? All right, so I'm going to count to 5, and I'm going to work through the problem. All right, here we go. Determine the percent viability and the cell density given the following data. A 0.410 mil aliquot of cells was removed for counting. And I just put this weird number in to emphasize the fact that we just need to remove enough of a sample in order to begin our counting process. So it could be 0.2, could be 0.3, it could be 0.33. It doesn't matter the size of the aliquot that we remove for the most part, as long as we don't deplete the entire culture. We just need enough to begin our counting process. All right. So we remove 0.410 mils, and of that 0.410 mils that we removed for counting, we then took 75 microliters of cells out of that aliquot and diluted that with 525 microliters of 1x PBS, right? So we had our original tube that we put the 0.41 mils in. Out of that tube, we took out 75 microliters, put it into the next tube, into a second tube, and added 525 microliters of 1x PBS. So now we have a second tube. We gently mixed that, and then we took 4 microliters of the diluted cell sample from that tube and diluted it with 4 microliters of trypan blue. So that's our third tube. And then we counted, in this case, just squares 1 and 3. And I'm not going through all 10 squares just to save time in this video. But in the lab, you really should count all 10 squares, unless the SOP or the boss says differently. Okay, so again, we start by counting the cells in squares 1 and 3. We're going to draw our little counting box right around square 1. We're going to then do our count, because you knew from the previous example to exclude the cells outside the counting box. And here in square one, I counted 23 total cells, 4 of which were dead or were non-viable, right? And then in square three, same thing. Mentally draw our counting box, exclude all the cells outside the counting box, count the cells inside. And here I got a total of 25 cells. And again, I got 4 dead or 4 non-viable cells. So if we look at our totals here, we have 58 cells in total, 25 plus 23. We have 8 dead, 4 plus 4. And then 50 live, just 58 minus 8 gives us 50 live cells. And here we only counted 2 squares. We now have enough information to do our calculation. So we'll calculate the percent viability. Again, we will write out the equation that we're going to use. Then we're going to plug and chug. 50 live cells divided by 58 total cells times 100%. Right? And that gives us a viability of 86.2%. Again, 3 significant figures, right, for our cell counting problems. Okay, so that was pretty easy. Hopefully you guys got that with no problem. And then let's calculate the cell density. Okay, so again, we're going to just write the equation that we use to calculate the cell density. Total live cells over total squares counted times our dilution factors times the hemocytometer correction factor 10 to the power of 4. Right, and so we have the PBS dilution, and here I'm not going to write them out, but we had 525 microliters mixed with 75 microliters, so our final volume there is going to be 600 microliters. Okay, and then we also have our trypan blue dilution where we mix 40 microliters with 40 microliters. Okay, so both of these mean that we have to, both of these are with, so we need to add the volumes together. Okay, so it's going to be 50 cells, 50 live cells, because remember, only live cells will divide when we passage, divided by just 2 squares, times 600, that comes from 525 microliters plus 75 microliters, that's our final volume, divided by 75 microliters of cells, times 80, that's 40 plus 40 divided by 40, times the hemocytometer correction factor. Do the math on your calculator, and we get 4.00 times 10 to the 6 cells per mil. Again, 3 significant figures. All right. Now, and one last thing is, notice in this problem, I didn't give you any information about the flask size. We don't know if it's a T25, a T75, a T225, right? If it's a shake flask, 1 liter or whatever, even a bioreactor. We don't need to know the flask size or the media volume as long as we know the dilution factors and have done the cell count. Okay. All right, now we're going to switch gears and sort of go in the reverse. And the idea here is that your cell suspension is too concentrated. We're not within our acceptable range of 20 to 50 cells per square. So how do we quickly estimate the appropriate dilution to get us back in that range of 20 to 50 cells per square? So here's the problem. All right, lots of words here just to get you used to understanding which information you need to use to solve the problem and which you can disregard. So we have a 0.35 ml sample of detached cells removed from a T225 flask containing 35 ml of media. 25 microliters of the counting sample was diluted to 100 microliters with 1x PBS. 50 microliters of that was removed and diluted with 50 microliters of trypan blue. We loaded the hemocytometer and we counted a single square, and we determined that there were 103 cells in this square, right? 28 of those cells were blue. All right, so the problem here is 1 square of the hemocytometer contains 103 cells. The optimal number of cells for accurate and precise, that is reproducible counting, is 20 to 50 cells per square. So just as an intermediate value, I said I'm going to try, my target is I'm going to try to get 25 cells per square. That's the target value to estimate a dilution. I could have chosen any value between 20 and 50. Could have chosen 20, I could have chosen 30, I could have chosen 35, I could have chosen 40, I could have chosen 49, but I chose 25. And generally, when I have to do this kind of calculation, I usually do either target for 20 or 25 cells per square, because if there's so many cells in that square, if the suspension is so concentrated, I've probably missed counting some of the cells. And so I want to go on the low end to put in the hemocytometer. Okay, so really you just look at this and say this is a conversion factor, 25 cells per 1 square, all right? Or 1 square per 25 cells, right? It's a conversion factor, so you can reverse the numerator and denominator. So it's just saying 1 square equals 25 cells, or 25 cells equals 1 square. Simple algebra here. Okay, so to calculate the dilution factor, all we have to do is say we're going to multiply 103 cells times 1 square per 25 cells. This gives us a value of 4.2, which is approximately 4, right? I'm not going to dilute to 4.12. I'm just going to dilute to 4. That's a nice, easy number to work with. Okay, and so that means I should dilute my cell sample 1 to 4 for counting. That is, take 25 microliters of cells and dilute it with 75 microliters of 1x PBS. So we have a final volume of 100. 100 divided by 25 is 4/1. Okay, or, I can do any ratio of that. I could do 100 microliters of cells with 300 microliters of PBS to a final volume of 400. So that would be 400/100, or again, 4/1. So any ratio that you want works. And on the very last problem, we'll give you some other kinds of ratios. So, how much you use to do the dilutions depends on how much material you have. What volume of cells do you have? Okay, so here's a couple other problems. You should try these, right? Pause this and then come back and see if your answers agree with mine. So again, I'm going to count to 5 and then I'll just sort of talk through the problems. Okay, I'm back. Here we go. A 0.28 ml sample of cells was removed from a T75 flask containing 16 ml of media and used for counting. 50 microliters of the counting sample was diluted to, right, so that's our final volume, to 250 microliters with 1x PBS. An 85 microliter aliquot of the diluted cells was removed and mixed with 85 microliters of trypan blue. And again, I'm just using different numbers to illustrate that as long as we obey the ratios, we're okay. After 2 minutes, we loaded the hemocytometer. We counted 2 squares. And over those 2 squares, there's 346 cells, right? I probably would have only counted 1 square. Once I saw that this was so concentrated, I wouldn't have wasted my time counting a second square. But for the purpose of the problem, we pretend that we counted 2 squares. 88 of the counted cells were blue. Determine the appropriate dilution for this sample. So again, same thing. Here, we know that we want 20 to 50 cells for accurate and precise counting, right? We're simply going to determine the dilution factor. This is going to be 346 cells per 2 squares, because we really want to go per 1 square, times 1 square with 20 cells, or we get a dilution ratio of 8.60. And so we could dilute this 1 to 8. Usually using even numbers is easier to work out the dilution, okay? But we could also do a 1 to 9 dilution, okay? And so to do this, the dilution scheme would be 50 microliters of cells to a 400 microliter final volume, which means we use 350 microliters of balanced salt solution as our diluent to dilute the cell suspension. And then example 5, 0.95 mils of detached cells was removed from a T25 flask containing 6 mils and used to count. We took 35 microliters of the counting sample, diluted it to 700 microliters with 1x PBS. We took 25 microliters of that diluted sample and mixed it with 25 microliters of trypan blue. After 2 minutes, the hemocytometer was loaded, 2 squares were counted, and a total of 82 cells over those 2 squares were counted. 6 were blue. Determine the appropriate dilution for this. So if you look at this, 82 divided by 2, that's 41 cells per square. That's in our range of 20 to 50 cells. So we didn't need to do a dilution, right? Just seeing if you're paying attention here. So again, the range is 20 to 50 cells per square. And in this problem number 5, we're already in that range, so we don't need to do a dilution. Okay, finally, 0.35 mils of detached cells were removed from 45 mils of media and a T225 and counted. 25 microliters of the counting sample was diluted to 100 microliters with 1x PBS. 50 microliters of that was removed and mixed with 50 microliters of trypan blue. We counted a single square, and we think that we counted 188 cells, but really you probably could not accurately count 188 cells in one large counting square, right? 8 of the cells were blue, determine the appropriate dilution. So this is the same thing. You guys should pause right now and see what you come up with. And also try to give me some values, that is the volumes of cells and diluent of PBS or HBSS that you would use to get this dilution accomplished. So counting to 5 and then coming back. Okay, so again, it's 188 cells per square. This is 1 square per 20 cells. That gives us a dilution factor of 9.4, which we can round to 9, or in this case, I would round it to 10, because I'm sure that I did not accurately count 188 cells in the square. I'm guessing there are probably more, and also 10 is just an easier number to work with when we're calculating dilution volumes. So we're going to dilute 1 to 10. One example of this could be 20 microliters of cells plus 180 microliters of PBS, right? That's 200 microliter final volume divided by 20, which is 10 over 1. But other variations, we could do 10 microliters of cells plus 90 microliters of PBS, 40 microliters of cells plus 360, right? That would be 400 over 40, or 100 microliters of cells plus 900 microliters of cells. So just pointing out that there are numerous volumes combinations that you could use to achieve a 1 to 10 dilution factor. And that is the end of segment 5.